So let's see. I think I'm recording, and I guess we'll start. This is Microbial Metabolism, Chapter 5, Part 2, and it's long and brutal. And so let's get started. Before we talk about it, a couple of concepts that I believe are helpful. You may or may not agree. These are the laws of thermodynamics. Anytime you're talking about energy, physics has something to say about energy, and a lot of what physics has to say is in these laws of thermodynamics. First law of thermodynamics is that energy can be converted from one form to another. Yeah? There's lots of kinds of energy. Do you guys know about kinds of energy? Raise your hand if you can think of a kind of energy. I got one hand up. I got 3 hands up. I'm going to start with Tori. Kinetic energy. Energy of motion, that is, yeah? Others. Potential energy. So potential energy is stored energy, energy ready to be released. Inasmuch as I have a baseball held up high in my arm, if I as long as I'm holding it, that baseball has potential energy. When I let it go, that potential energy is actualized as kinetic energy, yeah? Yeah. Mechanical energy, sure. The energy of moving levers and so on, yeah? Any other kinds? Solar energy, yeah. So that's radiation energy. So if you use a solar powered car, thank you. You could use the rays of the sun, right? Can be converted from solar energy into mechanical energy inside the car, which can be converted into kinetic energy as the car moves. Does that make sense? Right? All right. So you have, in this discussion, it is clear that you guys can think of others. The rest of you who have not raised your hands, are you familiar with these concepts of kinetic energy and so on? Other kinds of energy, yeah. Gravitational energy, yeah. So again, gravity can be used to power. Well, I don't know if it powers things, but it's sort of the cause of the potential and kinetic energy that we talked about previously, yeah? So there's several different kinds of energy, and those kinds can be interchanged and interconverted, yeah? We can convert solar energy to mechanical energy to kinetic energy. We can convert chemical energy to potential energy to kinetic energy and so on. The second law of thermodynamics is that anytime you convert one energy from one form into another, there's always some loss of energy. And that loss of energy is usually lost as heat. This is energy interconversions are never 100% efficient. There is energy lost, and this energy is described, this phenomenon is called entropy, the tendency towards disorder, the tendency of things to move towards a ground state of less energy, yeah? That doesn't mean that energy can ever be converted created or destroyed, right? Energy cannot be created from nothing, but it can be interconverted. Nor can energy just disappear. When energy is lost, that is usable energy is lost, but unusable energy is still there, right? The amount of energy that's converted is still completely converted, just not converted the way we want it to be. Am I making sense here? Let's look at some examples. So here's some really nice examples that I think are relevant to today's lecture. So that's why I include this diagram. So we've got a river, a flowing river, right? Energy itself, if we want a definition of energy, it is the ability to do work. And that essentially is to move stuff, move massive objects, move things that weigh something, right? Can a river move things? Yeah, you can imagine rocks on the bottom of that river being tumbled by the current of the river, yeah? If there's a rain, the strength of the river's current increases, and the rocks are dislodged from the bottom of the river, and they tumble down with the flow of the river. Yeah? And then once those rocks tumble, they squish things, right? There's a bug on the bottom of the river, and it would get squished by the force of that rock when it rolled over it. Yeah? So the river is doing work. You agree? Right? So, can that energy be converted? It can. That river, and it looks like my laser pointer is doing absolutely nothing, and the batteries must be completely dead. But if we put a dam on that river, right, the river is no longer moving, yeah? Has the energy been destroyed? No, the energy is still there. The energy of the river has been stopped, but it hasn't disappeared. What do we call the water's energy now? It's potential energy, yeah? And we can tap into that potential energy by doing what? Well, we put a little powerhouse in the bottom of the dam, we put a little hole in the bottom of the dam, and we let water leak out through that hole. And when water leaks out through the bottom hole in the dam, it doesn't just trickle out. It squirts out with the force, the gravitational force of all the water sitting on top of that hole. Does that make sense? And so it doesn't just trickle out, it squirts out, and when it does, you can put a turbine there. Do you guys know what a turbine is? It does. A turbine is essentially the same thing as a windmill. Yeah? And when the wind blows, the windmill turns around. This is a different fluid from air. This is water. And as the water flows past, it acts like a very high-tech water wheel. You guys know about a water wheel, right? That's another way to capture the energy of a flowing river, isn't it? You agree? Right? So in this case, the water wheel spins, and as it spins, its axis that it's spinning on spins. And when that spins, we can put some magnets on that spinning axis. And those magnets, when they go around, we can put another ring of magnets around the first ring of magnets. And as those magnets rub against each other, electricity is generated. And when electricity is generated, we can send that electricity off to your house. Yeah? And at your house, when you plug in your lamp, the energy from the dam is converted into light energy. Yeah? And then that light energy can illuminate your room. Is that clear? All right. But at each step in this process, there is some loss of energy. The amount of energy, potential energy, in the dam does not equal the amount of energy stored in the batteries, the motor, or given off in the light, right? These three together are less than the energy that was behind that dam. You guys understand? And that means some energy was lost in the process, yeah? And the light really serves as a good example of that, right? The light, what happens when you touch it? You feel that it's hot. If it's an incandescent light bulb, you'll burn yourself. And if it's one of those complex fluorescents, well, you won't burn yourself, but it will be warm. Yeah? Was this light turned on in order to heat the room? It was not turned on to heat the room. It was turned on to illuminate the room. Yeah? But it took energy to heat it up, didn't it? Right? So that's energy that was spent on heating the bulb rather than illuminating the room. And we didn't want to heat the bulb. We wanted to illuminate the room. Does that make sense? So that heat energy is a good measure of energy lost in the conversion all along here. If we touch this wire, along with getting zapped, we'd also notice that the temperature of the wire was warmer than the ambient temperature of the air. Yeah? So we're also heating up this wire. We don't want to heat up the wire. We want to send electrons through the wire so that we can get to people's houses, right? So as the electrons flow, there is some loss of energy. Yeah? Guys good? All right, so we've learned about the interconvertibility of energy, the persistence of energy. Energy is neither created nor destroyed ever, but energy can be interconverted, and when it is, the second law says that there's always a little bit of energy lost, right? And that energy does not disappear, it's just not going where you want it to go. All right, so water behind a dam, what does that represent? Potential energy, stored energy. Okay, and stored energy is relevant to today's discussion. Okay, so most chemical reactions involve exchange of covalent bonding partners. So here we can see that there is energy in chemical bonds. Chemical energy is stored, is a kind of potential energy, yeah? And is there energy in one of these? So we have a chemical reaction. Hydrogen gas combines with oxygen gas. We give it a little spark, and water is formed, yeah? So if that's the case, then these hydrogen bonds and these bonds holding the oxygen atoms together are traded for bonds between hydrogen and oxygen, yeah? You guys understand? Okay. And in that exchange of covalent bonding partners, there's an exchange of energy. And if energy is required for this to happen, then we say the reaction is endergonic. And when the energy is given off in a reaction, we say it's exergonic. You understand? Do you guys know if this chemical reaction is endergonic or exergonic? Endergonic requires energy. Exergonic gives off energy. How the heck would you guys know? Yeah? You're probably not familiar with the reaction, but here are a couple of examples of the same reaction. The reaction is reversible, right? Which means the reaction can go either direction depending on the conditions in which you put the species, yeah? So, can you see little bubbles coming off of this glass of water? And what are these wires connected to, would you expect? Right? These are wires. They're connected to these clips. Where are these clips going, do you think? Some kind of power source. So this reaction, what are these bubbles? Oxygen. What else? Hydrogen. So is this reaction in this picture going from the left to the right or the right to the left? It's going from the right to the left. Water is being converted into hydrogen and oxygen gas, yeah? Is that exergonic or endergonic? Is energy given off or required? Energy is required, right? We see that because energy is coming in from the battery, yeah? Does that make sense? So in this direction, energy is required, yeah? And it's endergonic, yeah? What about this direction? Have you guys seen this picture? If you have your Led Zeppelin album covers, then you've definitely seen this picture, yeah? This is the Hindenburg tragedy. Have you guys heard of this? This is a gigantic blimp, yeah, a Zeppelin. What's inside? Hydrogen gas, yeah? And what's happening? There's a huge explosion. Why is that? Well, there was a spark, yeah? And the spark caused the hydrogen in the blimp to react with what? Oxygen in the atmosphere, yeah? The atmosphere is full of oxygen, and so we see an explosion and tragedy, yeah? Are you guys familiar with this? How many people have heard of this historical event? I think 1933 or 1934, something like that. Okay, so it was certainly a very bad idea to fill the blimp with hydrogen instead of helium, yeah? Helium doesn't burn, hydrogen gas does in the presence of oxygen, yeah? I think they did, and they just somebody made a bad decision. They said, well, we don't have any helium around, and we really want to show off this awesome blimp. What the heck, let's just fill it with hydrogen, right? They certainly knew. They had Nobel Prize winning chemists there. This reaction was known since at least since the early 19th century, the early 1800s. A French chemist, Lavoisier, separated out the gaseous constituents of a water molecule you know, before he got his head chopped off in the French Revolution. Yeah. Yeah, so clearly the people below here, there would be water created. Yeah, there would be mist or rainwater coming down from this tragedy. And in fact, if you hold your hand over a Bunsen burner, right, your hand will start to feel moist because water is a product of the combustion of, and if you ever see water coming out of somebody's tailpipe, a lot of that is condensation in an early morning, but there's water coming out of a tailpipe when the engine runs normally, yeah? So that chemical reaction, right, the chemical reaction in our Bunsen burners is methane, CH4 plus O2, CO2, and H2O, yeah? And as far as balancing this reaction, let me see. I've got 4 hydrogens. I think it's 1 CO2. I got 1 carbon, 4 hydrogens, 2 oxygens. This is 2, 3, 2, and 8, 4. Is that right? 6. Oh. It's been a while since I had to balance this one. Hold on. I think isn't this like 1/2 here? No, that can't be right. 2 hydrogens on the right. And I got 4 on the left. 2. Are you enjoying watching me suffer here? 2, 4, 2, 4. Boom, that's it. All right. Thank you, Michael. Thank you. All right. So, and there it is, right? Water is a product of the reaction, right? When we use our Bunsen burners, water is formed, yeah? Why don't we see the water? Because it's very hot when it's formed. It's a gas when it's formed, and it becomes water vapor, yeah? But again, it'll condense on your hand if you hold it a safe distance. Safe distance, please, above the burner flame. Do not touch the burner flame. It's hot, you know. Okay, is that clear? All right. So we've learned about exergonic and endergonic. We've learned about the reversibility of chemical reactions. And we've learned that energy is involved in the exchange of covalent bonding partners, yeah? There's energy in chemical bonds. And when bonds are broken and reformed, energy can be absorbed or released. Now let's look at this graph here before we move on, right? So, is this reaction exergonic or endergonic? As it's shown with hydrogen and oxygen coming together to form water. Exergonic or endergonic? Exergonic, right? We saw that in the pictures of the exploding blimp, yeah? All right, so it's exergonic. So, can you see this graph here? The x-axis of this graph says reaction coordinate. The y-axis says energy, yeah? So, here is, on the left, what it says, reactants and products. So, effectively, reaction coordinate is the progress of a reaction. In effect, turning hydrogen and oxygen into water, yeah? So, does this graph depict an exergonic or endergonic reaction? Can you tell? There's 2 lines, but they both start in the same place, they both end in the same place. So both of them are either exergonic or endergonic. Which is it? Exergonic is correct. Do you guys see how that is? If you don't see, you'll get plenty more chances. We'll look at this graph again, but let's just look at it for a second here. What's What do we say about these reactants? Well, they have this amount of energy. What about the products? They have a lower amount of energy. What about the difference between this level of energy and that level of energy? The difference between them is the amount of energy given off in the reaction. In the case of the Bunsen burner, that represents the flame. In the case of hydrogen and oxygen forming water, this represents the explosion of the Hindenburg, the difference between here and here. You guys get that? You guys understand that? Okay. So we'll see that again. All right. So how about this question? Which molecule pairs have more energy in their chemical bonds, A or B? So this represents the combustion of gasoline in a car's engine, yeah? So we put the gas in, we turn on the engine, oxygen from the environment is sucked in by the engine. The engine sucks in the oxygen, and then the car goes, carbon dioxide and water is released. So the number of atoms never changes. We have carbon, hydrogen, oxygen. On the right side, we have carbon, hydrogen, and oxygen, yeah? So the same atoms going in, the same atoms coming out, but the amount of energy in the covalent bonds holding the atoms to each other here and holding the atoms to each other here is not the same. Which molecule pairs have more energy in their chemical bonds? Now, everybody raise your hands before you shout out answers. And then while you're raising your hands, if you haven't raised your hands, think about it. Right? Try to get the right answer. All right, I got a lot of hands up. Hopefully everyone's had a chance to think about it. Which pairs of molecules have more energy? Yeah. People are saying A, unanimously, yeah? And if you didn't raise your hand, hopefully you were thinking A, yeah? Does that make sense? The gasoline is an energy-rich molecule. That's why we're putting it in our gas tank, yeah? Because we need that energy to make the car go forward, yeah? Here is our chemical potential energy being converted into kinetic energy of a moving car, yeah? Is all the energy from the gas turned into a moving car? Definitely not, right? Put your hand on the engine after you've been driving for an hour and see where some of the energy went to, yeah? It went to heating the engine. We don't care about heating the engine unless we're in New England and it's super cold and we use the engine's heat to heat up the inside of the car so we're not freezing while we're driving. But apart from that, right, the engine of the car is generating far more heat than it is generating kinetic energy of motion. The efficiency of a internal combustion car, do you guys know how efficient they are? You know what percentage of your gallon of gas goes to moving the car? I think it's like somewhere between 20 and 30%. It's pitifully low. All right. So, what about a cell? A cell is not a car, but there are some similarities, aren't there? This molecule is not gasoline. Do you know what it is? Probably pretty hard to recognize it just looking at the atoms like this. This is glucose. 1, 2, 3, 4, 5, and then there's a sixth. This is carbohydrate, yeah? And this is oxygen, and this is CO2, and this is water. And this is a cell. What's being made here? Any guesses? This is ATP, the energy currency of the cell. So we're using food to make ATP so that the cell can do stuff. Yeah? Which set of molecules has more energy? The ones on the left. In the same way that the gas is the energy for the cell. Yeah? You guys got it? And how efficient is the cell compared to an internal combustion engine? How the heck would you know that? Well, I heard the answer somewhere, and as it turns out, the efficiency of a cell is not much more efficient or less efficient than a car. It's about 20 or 30% efficient, right? And when we burn energy, what do we generate? We generate lots of heat, yeah? And that heat is dissipated off when we perspire and when we release heat to the environment, yeah? Is that clear? Okay. All right, so wouldn't it be nice if automobile engines could be more efficient? Well, they are getting more efficient, but it's a pretty hard gig to make a car more efficient than it is. Cells can't seem to do it. A cell that could be 10% more efficient would have a huge advantage over evolutionarily over cells that weren't, and yet they're not. Yeah, so evolution has failed to engineer a cell to the efficiency standards that we have also failed to generate in a car. And I don't know what to make of that, but I think it's interesting. Okay, so how does this happen? Well, in order for gasoline and oxygen to combine to form carbon dioxide and water and give off energy, in order for hydrogen and oxygen to combine into water to form energy, well, those molecules have to touch each other, yeah? They have to crash into each other. This is collision theory. I think I included this in your homeworks, yeah? The textbook talked about collision theory. You guys remember answering something about this in your homeworks? Yeah. According to collision theory, exergonic reactions happen on their own, but not without sufficient energy. In order for any chemical reaction to happen, right? If I open this valve, right? Was there any sense of danger as I opened the valve? Right? And so gas is pouring out into the classroom, yeah? We're all going to die. We might be in danger if I kept it open for a long time, right? But just opening it for a few seconds, right? Isn't that flammable gas? It is flammable gas. Come blasting out of the nozzle. So it's supposed to combine with oxygen, right? And there's oxygen in the atmosphere. So I just mixed methane gas with oxygen, and yet there was no explosion, yeah? Needs a spark, lacking sufficient energy. We need to separate the oxygen molecules from each other. All of you guys are giving me various versions of a correct story, yeah? And that is that in order for the methane to react with the oxygen, they have to A, crash into each other, but B, they have to crash into each other with sufficient energy. Two cars going 1 mile an hour bump each other's fenders, no damage, right? Two cars going 20 miles an hour bump each other's fenders, you got some damage there, yeah? So to some degree, it has to do with the amount of kinetic energy of the molecules themselves as they A, bounce into each other, and B, bounce into each other at a certain orientation. So one other point in this is that if I get T-boned at 1 mile an hour instead of bumping head-on with my bumpers, right? Well, one of those cars might get more damage than the other, yeah? So depending on the orientation of the cars as they collide is going to determine to some degree how much damage gets done. Likewise, the way molecules crash into each other with enough energy and with the right orientation, there's a reaction or not. Does that make sense? And here we can see what's called the energy of activation, the amount of energy needed in order for the reactants to be converted into products, yeah? So this represents the energy to, as Michael put it, separate the oxygen atoms. This represents the sort of literal term that Netta used. And this, as David said, represents the energy of the spark that's needed to make the reaction happen. Does that make sense? So all those three terms describe this, right? Which is needed to, in order to take these reactants and convert them into products, we need to invest this much energy, yeah? Guys got it? Okay. And then, once that energy is invested, the products are created, and we get this much profit, so to speak, to talk in money terms, yeah? Is that clear? All right. So ATP is an energy currency that serves as an interface between the food that we eat and the stuff that we want to do, the actions we want to do. Yeah? Yeah. Yeah. Oh yeah, so the one with boxes around it. So there's a bunch of, first, can I just tell you a problem that I have? Let me see, what do I got here? This looks way better than what I'm working with. Okay, so I'll see if I can pull this up, but this is what I sent in, and I guess maybe for printing, they printed it, and then what happened? Yes.